we had just stated that the question was asked, do we ever have to resample the swings? The answer is, in this data set, no, because the swings are all clamped to specific values. And so the question was then asked, well, what's the point of this inverse gamma distribution over here? Does it affect anything? The answer is yes, it does, due to the principle of explaining away. Essentially, if you look at the golfer error, the Markov blanket for the golfer error includes its parents, which is that inverse gamma distribution up above it, and its children, which are the swings, which are clamped to known values, and the parents of those children, which include this inverse gamma distribution over here to the right. And the point I'm trying to make is when it is important to resample all of these nodes, because as the inverse gamma distribution that is the parent of the swings changes, that explains away some of the swings that could affect the golfer error. That didn't come out as clearly as it did a moment ago, but in short, when you resample the swings, just use the clamped value as specified in the data, because we know this value. But you do have to resample all the other nodes, otherwise you won't get the right answer. Basically, the only thing that is clamped is swings. I can't think of anything else that we know, because the golfer name doesn't appear in this graphical model. The tournament that they participated in is in the data set, but that doesn't clamp anything. That just tells us which of these tournament difficulties is connected to that node below of swings. Yeah, okay. So really, the tournament number is there to specify the connectivity of the graph when you construct it. The only thing you'll use at training time when you're resampling this whole network is the number of swings, and that clamps the value of this bottommost node in the graph. And everything else will be affected by that until it converges to useful values, and finally golfer error is the thing we're interested in. I want to talk about a continuum from naive. Have you ever heard of naive Bayes?
In your book.
In my book. Oh, okay. Well, thank you for reading. All the way to Bayes optimal class. It's not written yet? Oh dear. Okay, sorry about that. Okay, essentially, naive Bayes is the world's suckiest classifier. That's a lot. People in the Bayes community will often refer to it as idiot Bayes, because they just really want to ding it with an air of bad-sounding connotation.
So it's a baseline.
It's a baseline. It's very much a baseline. But what's interesting is it's a lot better than the baseline we usually use of the most common classification. Naive Bayes is, one of the reasons they try to malign it so much is naive Bayes is often considered synonymous by people who don't know anything about Bayesian statistics with Bayes. Basically, naive Bayes has become the standard of Bayes learning. And a lot of people will even call it Bayes learning. And the Bayesian community will get all up at arms about that and say, hey, naive Bayes does not represent us. And they're really trying to distance themselves from naive Bayes. Suffice it to say, naive Bayes is super easy to code up. It's taught as one of the standard machine learning algorithms in any machine learning class. It's blazing fast for learning. It's been used for spam filters for many years because it makes a really good spam filter. It can be trained incrementally. It has a lot of nice properties. If we were to draw it in terms of a graphical model, I'm going to use the letter C for a classification, and I'll use the letter, how about F for features. We're going to assume that for every point in your data set where you have n training data points, every set of features that you get is caused by the class label. So for example, here's plate notation of a Bayesian graphical model, but essentially you're classifying the, what are we doing? Let's say we're classifying pizzas as being tasty or yucky, right? So C can take on the values of tasty and yucky. And why is it tasty or yucky? That seems kind of backwards, doesn't it? It's the features that cause it to be tasty or yucky. Let's use a better example then. Let's use the example of iris flowers. So you have an iris setosa or an iris versicolor or an iris, what's the other one? There's a third one in that data set. The iris data set's a very famous data set. You have 3 types of flowers. Then you go and you measure the petal width, the sepal length, the petal length, and the other thing. So you have 4 values that come from the flower, and presumably the length of the petals and the length of the sepal are a product of the type of flower that it is. This one makes more sense, right? That the measurements are caused by the class, doesn't it? Or if you're doing, let's suppose you're trying to figure out the gender of people based on their height and their shoe size or something like that. Well, the gender's already fixed. That's the class. And the features, the height and the shoe size, are kind of products. They're induced by the class. And therefore, we model it like this. Now, usually with naive Bayes, we assume the class is categorical and the features are all categorical. But they don't need to be. You can just as well make the features be normal distributions or any other distribution you want. In fact, they almost always make the class categorical. But unbeknownst to you, you have implemented naive Bayes classifier in this assignment. Because if you just build that structure and sample it with your data, you'll get the exact same results as naive Bayes classifier. It turns out this can reduce to just a few lines of code where you actually just count up the proportions of values. And with a little bit of math, you can just make a little table and build a naive Bayes classifier. The thing with naive Bayes classifier is every time you get a new sample, you're just adding another node to your graph, right? And you do a little bit of resampling. It may slightly affect things. But you can do the math in closed form, and because of that, it's just a really standard way to sample everything. Okay, so there you go. That's naive Bayes classifier. Any questions? Okay. I don't like naive Bayes classifier because it doesn't give very good accuracy compared to other learning algorithms. It always seems to beat the baseline. In fact, it's a very reliable classifier. It's very involatile. It gives very solid, consistent results. It consistently doesn't suck too bad, but it's worse than decision trees and neural nets and just about everything else at any interesting problem. Okay. By contrast, Bayes optimal classifier, a little harder to draw, but let's suppose, so Bayes optimal classifier considers all possible hypotheses in the entire hypothesis space. Let's suppose there are m of them. So if we were using neural networks, this would mean all possible neural networks, meaning all sets of weights that you could possibly assign to them. You see that's kind of intractable, right? But if you consider all possible hypotheses, and remember each of these circles is parameterized by its probability distribution. So these pictures can be deceptively simple. And up here in naive Bayes, when I draw the C here, I'm assuming you know the prior probabilities, the prior probability distribution of each class label. And the F here, there's also parameters here that specify the distribution of those features. And usually we draw those distributions by just sampling our training data and measuring the likelihood of each possible feature. Okay. Likewise, when I draw a circle with an H in it right here, that implies that not only do you know all the hypotheses that are possible, by hypothesis I mean a function that takes features as inputs and outputs the class label, but you also know their distribution. And that's something that's not known. So if you knew the likelihood of every hypothesis, if you even knew every hypothesis, that would be extraordinary. But if you knew the likelihood of every hypothesis, that would be profoundly extraordinary, right? So already I think you can see that Bayes optimal classifier is pretty much impossible in most situations. It's a theoretical construct, but it's one that is very interesting and useful in theory, so that's why I'm talking about it. So the actual class that we want is going to be a product of the hypothesis we choose and the features that we have to work with, right? So the graphical model is going to look something like this. And well, we're kind of suggesting that the class label is a function of whatever features you have to work with and the current and the true hypothesis.
What if your hypothesis learned features, learns its own features?
Yeah, so in code, yes, hypothesis is always a function of features. So features are going to be fed into the hypothesis to generate the class. But in this case, I'm drawing arrows to class to imply that the class depends only on the features and the hypothesis. In other words, 2 arrows going into it implies there is some function here, and that function would actually apply the hypothesis. Is that clear? So yeah, don't think of this as a flow of information graph. This is a dependency, a probability dependency arrows. And that can be confusing, but well, it is what it is. Finally, we have some training data. Suppose we have n samples of t training data. And there's some accuracy that will be achieved from every single hypothesis, right? Now, I'm not 100% certain I drew this graphical model correctly, but I think I did. Essentially, what I'm saying here is, given that we have some training data, that'll say something about how good this hypothesis is, right? And there's a whole bunch of hypotheses. And if we visit all hypotheses and see how well they do on our training data, we can infer from that how much to trust each hypothesis when considering these features in order to predict this class label. Okay. Well, as impossible as this is, a bunch of statisticians and Bayes experts have analyzed this and have concluded this is not only an interesting thing to do, this is the thing to do. This is the, I don't know how else to put it, this is the correct answer. Meaning, given what you know, God could not predict a better thing from, if we limited God's knowledge to the training data, he could not predict a better class label than this thing would. Did that come out right? Unless, of course, he's magic, which, you know, that changes everything. But the point is, this is not merely a good thing to do. This is the definition of correctness, meaning this utilizes all possible information given that we assume that this is all your information. And therefore, it follows that no better classifier can ever be built than Bayes' optimal classifier, in theory. Okay, you see why we want to study Bayes' optimal classifier, because if we're trying to build the world's greatest machine learning algorithm, we'd kind of like to steal properties from this, even though this is an impossible thing to ever achieve. Okay, so let me point you at a symbols. Ensemble averaging, I want just ensembles. Maybe it's ensembles. All right. Ensembles, machine learning. Google, please find me the right Wikipedia page. Ensemble learning. There we go. Hey, Bayes optimal classifier. Okay. Here's the true equation for Bayes optimal classifier. And this is a really interesting equation because this is the world's best machine learning algorithm. All we have to do is, where should we start? Let's start on the far left side. So y, this is the output we're trying to get, is the argmax. Do you remember what argmax is? It's saying, yeah, we're going to say find the C that maximizes this whole equation. So whatever this equation gives the biggest number to, that's the best C, the best class label that we could possibly get. So we're going to visit all possible class labels. Presumably this is categorical. If it were continuous, then I guess we have to visit all of an infinity number of class labels. But for each categorical class label, we're going to basically measure its quality here, and whichever one has the best quality, we'll pick it. To do that, we have to visit all hypotheses in the entire hypothesis space, and we're going to sum over them and multiply by the probability of that hypothesis being the right one. I think you can kind of see intuitively that if there was a distribution over hypotheses, following that distribution is the right way to use a hypothesis, right? Imagine that one hypothesis was known to be true. That's the one you would use, right? Yeah. So if this distribution is the delta function, it's some Dirac delta that gives infinity weight to one hypothesis and 0 weight to all the others, this is essentially saying, use the true one. And if there's two that are equally true, and there's no way to differentiate between them, then it's going to use them both with 50% weight. Does that make sense? So we're saying visit all hypotheses, and for each one, compute what the class is and weight them according to their distribution of being correct. And the math over here is derived using Bayes' law to essentially say give the weight of each hypothesis what it should have. And this is why Bayes' optimal classifier is the optimal classifier, and nothing can beat it in theory, because if you're beating it, you're doing it by cheating somehow, or you're getting lucky, or you're, et cetera. Okay. So we're going to take the probability of each class given the hypothesis. Read that. Multiply that by the probability of your training data that it would come out of that hypothesis. Can you think about what that means for a minute?
The probability of your training data?
We're saying, so right now we're looking at one hypothesis, which I'll call high, because H sub I. Now, if high is the true hypothesis, meaning if that H is the same as the model, same as the universe that produced your data, then we could ask how likely is this training data to have emerged from that universe? And presumably a good hypothesis will produce the training data you actually see.
Okay.
So this is a measure of how good your hypothesis is from the training data you have to work with. Okay. Finally, we have to multiply that by the prior distribution over all hypotheses, which is something no one would ever possibly know. It's a completely irrational term. Nevertheless, you can implement Bayes' classifier for really, really, really tiny toy problems, and it will take hours to compute your class, but you can do it, and if you do, no machine learning algorithm will ever beat it. And so I think that's kind of an interesting thing to look at. Something I've never seen done or heard of done before is building a graphical model for Bayes' classifier and then just sampling it for a darn long time and see what happens. Probably should have worked that into the assignment, just because that'd be darn interesting. But I don't know. There's a area that I think may be open for research, is what happens if you build this graphical model, and what if we look for a hack to fill in the things that we can't possibly know? For example, you can't possibly know the prior distribution over hypotheses, but what if we do something? Yeah, what if we throw numbers at it? What if we try something? It seems like this isn't an impossible, I mean, this is a pretty simple graph, right? And you have the code that can sample arbitrary graphs, so given enough samples, it seems like it should do something right. I don't know. At least in theory, you have now coded up the world's best machine learning algorithm, so there's got to be something to do with that.
How big is the space of all the possible?
Well, here's the problem. Your training data is reasonably large, right? So there will be a lot of sampling there, but we've done that in this assignment. This is the killer. How big is the space of all possible hypotheses? What do you do? I don't know. So yeah, on the other hand, maybe we can just throw out bad hypotheses, right? If you take a neural network and you train for a darn long time, the only ones we would consider are the ending points, right? You wouldn't want to take all the initial weights hypotheses, because that's just dumb. So maybe you train a neural network 20 times, and then you ensemble them in this way. So we're going to basically take 20 trained neural networks and then measure how likely the training data is to come from each of them. And that will produce a pretty strong ensemble. So what we're really kind of looking at here is ensemble theory. Do you know what an ensemble is? The idea is you take a bunch of trained machine learning algorithms or a bunch of hypotheses, and we want to figure out how to combine them together, how to make them vote on the final answer and get the optimal final conclusion. So essentially what I'm tiptoeing towards is, hey, we've learned a bunch of AI and machine learning techniques. Turns out you can combine them to get even better accuracy. And I think there's a lot of important AI concepts dealing with how to make AI interact with AI in order to achieve yet greater AI. It's been said that humans are more intelligent in societies than they are as individuals. And therefore, AI should be built of a whole bunch of AI components, and there's interesting things to study there. And apparently I only have 1 day left in which to teach that, but see what I can cram in tomorrow. Out of time, thanks for coming.